So we've talked about how to interpret functions as rules, and that's really how you should think about them. Think of them as machines that turn input values into output values, right? So you plug in an input value and then the function will turn around and give you back an output value in return. So it's also useful to visualize the relationship between the input values and the corresponding output values. And to do that, we use the function's graph. So let me remind you about a few things. So the Cartesian plane, that's just a fancy way of saying the xy plane. Or you can remember when you take the two axes, the x and y axis, and put them together? That's the Cartesian plane. So formally, what it is, it's the set of all possible points that you can draw. So a point looks like this. You've got two numbers, two real numbers, a and b is the labels that we've used for them, and they're separated by a comma with round brackets around them. Now that's not to be confused with an open interval. The notation looks the same as an open interval, but you have to be able to tell the difference by context. So in this case, you can see right before the pair of values a and b, you see the word point written. So that's what clarifies, okay, this is not an interval, it's a point. And in particular, let me add something else. That first number, a, you interpret that, or we sometimes call that the x coordinate. And then the second number, b, we'll refer to as the second coordinate or the y coordinate. Now that's not universal, but it's going to be useful for our purposes, so we're going to go with that convention. So, okay, here's an example. Let's sketch the Cartesian plane. So we're going to draw two axes of basically two copies of the real line, essentially, just joined at the point 0. So they both have a point 0. That's going to be this point here, which we refer to as the origin. So you can sometimes write capital O for the origin, or maybe you might just choose not to bother writing that, because let's face it, the more things you draw in a picture, the messier it can get and the harder it can be to read. So sometimes you'll just take it to be understood that that's called the origin, the point where the two axes intersect. And then I used to be really picky about this, to be honest, but now I've gotten less picky over the years. You can label these axes as the x-axis and the y-axis if you like, but it's not strictly mandatory, as long as it's clear which one corresponds to which variable, because typically you'll have one axis corresponding to each of two different variables. What is generally true, almost always true, is that the horizontal axis will correspond to the independent variable of a function, the input value, and the vertical axis will correspond to the dependent variable of a function, or also known as the output variable. Okay, so that's the Cartesian plane. Oh, I skipped something, by the way. The notation for the Cartesian plane, you see it's written right here. That's just the blackboard R, so the symbol for the real numbers, but then you just put an exponent of 2 on it. It's not really like an exponent, it's just notation, but it just means two copies of the real line put together. But that's a short way of writing down the Cartesian plane. So you may see me sometimes write it up here just as a reminder, as a label. But again, if you omit it, it's not necessary. Okay, enough blabbing. We're asked to do something. We're asked to plot 2 points. The first point is the point 1, 3, and then the second point is the point negative 2, 4. So let's start with the first one, 1, 3. So let's start by labeling some values on the x-axis. Let's call this 1. I could label this 2, 3, 4. What's going to be the problem, though? If I put too many labels, again, I'm going to run into the problem where it's hard to see what's going on. So sometimes you'll just label a couple. If I put a 1 there, it's obvious. It's kind of understood that the other 3 would represent 2, 3, and 4 respectively. And actually, I'm going to put the 1 a little closer to the notch. Okay, so that's on the x-axis. Let's do the same thing on the y-axis. So 1, 2, 3, 4. And it doesn't have to be perfectly to scale, but you want to do a reasonable job of drawing things to scale, but sometimes you won't be able to make it perfect, right? Especially if you're just drawing these things by hand. Graph paper always helps. Okay, so to draw the point 1, 3, our x-coordinate is 1, and our y-coordinate is 3. So the way we're going to do this is we're going to go find 1 on the x-axis and find 3 on the y-axis, and then basically just play battleship, right? That would aim you right to this point. Oops, now it's going to take forever to get rid of those. But that's going to give you this point right here. So that is what the point 1, 3 looks like. And then what about the other point over here, negative 2, 4? Okay, so the x-coordinate is negative 2, and then the y-coordinate is 4. So let's find negative 2 on the x-axis. I'll just keep going with the scale that I've already set, and it would make sense that this notch here would be -2. And then, so we'll count 1, 2, 3, 4. So this is the 4 on the y-axis, so that's going to tell us to put the point over here. So that'll be the point -2, 4. And you notice I've written the points directly on the graph, but that's not necessary. But since we didn't have much else to put on the picture, there's nothing wrong with doing that. Okay, so that's how you can sketch points. Quite often, though, what we usually want to do is you want to look at a function and you want to graph a whole bunch of points. You want to graph a whole bunch of points that, or I should say, you want to sketch a whole bunch of points that satisfy a certain property. And that is, well, you'll see in the next definition. So the graph of a function, so as soon as you have a function that takes input values from the real numbers and gives you back output values in the real numbers, then you can draw its graph on the Cartesian plane. So what is its graph? Well, it's a set of points. It's the set of all points that satisfy a certain condition. So what is the condition? Okay, so it's the set of all points of this form. So in other words, it's got to look like a point, right? You've got to have an x coordinate or a first coordinate, and you've got to have a second coordinate or a y coordinate. But the property that that point must satisfy to be on the graph of f is this property right here, which says that if you take the first coordinate, a, and you plug it into the function f, then you're going to get back, as a result, whatever the second coordinate was. So that's the difference between a point that's on the graph of f and a point that's not on the graph of f. Let's say really this is what you need, right? You need to be able to determine, if I give you a point, let's say the first coordinate is a and the second coordinate is b, for some choice of real numbers a and b. Let's stay as general as possible. How do you determine whether how do you determine whether that point is on the graph of f? Well, take the first coordinate and plug it into the function and see if you end up getting what the second coordinate is. And if the answer is no, then that's simple. That point, throw it away. It's not on the graph. But if the answer is yes, the result is the second coordinate b, well, then that means that point is on the graph. But that's not normally how you draw a graph. People don't just start throwing points at you and you say, yes, this one is on the graph, and this one's not. This one is, that one's not. That's not typically what you do. What you do is you pick some choices for the first coordinate, and then you plug them all into the function to figure out what the corresponding second coordinate would have to be for the point to be on the graph. And what you're doing when you do that is you're making a table of values. So let me remind you how to do that. Okay, so here's a function. Here as a problem, we're asked to sketch the graph of each function. It says using a table of values, and I'll remind you what that means. So, okay, here's the function. The function f is defined by, if you plug in an input value x, it's going to multiply that input value by a half and then subtract 1. Okay, so what we're going to do, I'll even start to draw a table here. So we've got an x column and a y column. And then I'll just draw a vertical line here to divide them. So let's pick some values for x. -4, -2, 0, 2, and 4. Now, those were, you might ask, okay, where did you get those numbers from? Why did you pick those exact numbers? It's like, well, I didn't have to pick those exact numbers, but here's my reasoning. I first of all, unless I have a really good reason to do otherwise, I like to pick a handful of values. I like to make sure 0 is one of them. And I like to make sure I got the same number of values on either side. So I got 2 numbers that are less than 0 and 2 numbers that are bigger than 0. But why did I pick multiples of 2 instead of just going -2, -1, 0, 1, 2? Because that would have been another option. But I chose to take multiples of 2. And the reason for that is because I've looked at the function f, and I noticed that whatever the input value is, it's going to be multiplied by a half. Right? You can multiply any number by half you want, but it's a lot easier if you know that the input value is going to be a multiple of 2. That will make your calculations easier. So that's why I'm choosing my input values to be multiples of 2, just so that things work out a little bit nicer when I go to work out the corresponding output values. So here's how we're going to do that. Let's plug all of these into f. So f of -4, we're going to have 1/2 times -4 minus 1 by definition of f, right? So that's going to give us -2 minus 1, which is -3. So that gives us the output value from -4. Plug in -4, you're going to get -3 as an output value. What about -2? F of -2 is going to be 1/2 times -2 minus 1. 1/2 times -2 is -1. Then we're going to subtract 1 again and you get -2. So that means negative 2 is the output value in that case. What about 0? F of 0 is going to be 1/2 times 0 minus 1. Well, 1/2 times 0 is just going to be 0, so you've got 0 minus 1, which is negative 1. You see what I'm doing? I'm just filling in the table like that. So let's got a couple more here. So I've got f of 2. That's going to be 1/2 times 2 minus 1. That's going to end up giving you 0. And then finally f of 4. You've got 1/2 times 4 minus 1. That's going to end up giving you 1. You can check that carefully if you want. Okay, so now the idea is you treat these as the x and y coordinates of a particular point. You put those coordinates together into a point and then plot it. So let's plot the point negative 4, 3, just like we plotted these points up on the previous example. Now we're going to put these together. So plot the point negative 4, 3. And since the example supplied us with a graph here, that's going to make things a little easier. So negative 4 is here, negative 3 is here. So that means we're going to plot the point down here. And then negative 2, negative 2. That's going to give us this point here. 0, negative 1, okay, 2, 0, and then 4, 1. And what you're hoping when you do this is you're hoping that you're going to see some sort of a pattern emerge that gives you an idea of the shape of the graph, right? And we did. Look at these points. They're all they're said to be collinear in the sense that you can draw a line that goes through all of them. So that kind of gives you a pretty good idea that the shape of that graph is a line. And we're going to talk more about lines in chapter 3. But I just want to remind you there's a couple of attributes that you always have with lines. The first part, well, almost always have, but for the most part you do have. There's a couple of exceptions, but we'll talk about those in chapter 3. But the two attributes that you almost always have, first of all, is the y-intercept, the place where the graph crosses the y-axis. Well, here it's negative 1. And guess what? Someone who's really good at talking about lines will recognize this and be able to tell you right away that that y-intercept is going to be negative 1 just from looking at the rule, the formula for the function, right? So that's how you could have known in advance that the y-intercept was going to be negative 1. The other key attribute is the slope. If I pick a point here and this point here, I can figure out the rise, the vertical distance between those points, and then the run, which is the horizontal distance between those points. And I'll be forming this right angle by doing that. So this is 2, and this one's going to be 4 if I measure it. The horizontal distance is 4. So that's the ratio of those two is going to give me the slope, which is usually referred to as, or remembered as, rise over run. So that would be 2 over 4, which is 1/2. Okay, and well, again, if you're good at recognizing function or good at recognizing lines from their formulas, you'll see, okay, there's a 1/2 right there. That's how I could have known that the slope was a 1/2. Okay, so we will talk more about those in chapter 3, but that's just a really brief reminder about how lines work. But also, more importantly, how table of values work, how a table of values works and how you can use it to get a visual picture of a function.